Hello, welcome to part 2 of our lesson on design of slender columns. So in part 1 of this lesson, we were able to look at certain introduction, then look at the issue of load combination, calculate the effective height of column, calculate the slenderness ratio of column, and then the limiting slenderness ratio. In this lesson, we are going to look into the actual design of slender columns, and then look at columns chart. So that is what we are going to look at in this part 2 of the video. So stay put and you will learn a lot in this particular lesson. So this is a design of slender column. Like a column is, we have established that a column is classified as slender if the slenderness ratio is greater than the limiting slenderness ratio. So the a slender column with lambda greater than lambda limb must be designed for an additional moment caused by its curvature at ultimate condition. So a slender columns introduce an additional moment to the primary moment that column was carrying. The additional moment is due to this curvature as a consequence of its slenderness. Now, Eurogrid 2 identify 4 different approaches to design of slender column. In this lesson, we will use the nominal curvature method. In this method, the second order moment are added to the first order moment. The first order moment is the original moment that is caused on the column due to the applied load, while the second order moment is additional moment due to the curvature of the column itself. So in this method, the equation for calculation of design moment are only applicable for columns of rectangular or circular section with symmetrical reinforcement arrangement. So a slender column should be designed for an ultimate axial load NED plus an increased moment given as the increased moment is given by this equation 6, which is MT. MT is NED times E thought. E thought is the total eccentricity. This is the applied design load on the column. E thought is the applied eccentricity or a total eccentricity. Now, total eccentricity is made up of 3 components of eccentricity. E naught, which is called equivalent first order eccentricity. EA, which is called an accidental eccentricity, which accounts for the geometric imperfection of the column, while E2 is a second order eccentricity. So once we are able to calculate these 3 eccentricity, we add them together to have total eccentricity. We come to this equation 6. We calculate the second order moment, which is the additional the total moment of the column. Now the equivalent eccentricity E naught is given by the greater of these 2 equations, 0.6 E or O2 plus 0.6 EO1 or 0.4 EO2, whichever is greater of these 2 expressions is taken as the equivalent first order eccentricity. In this equation, E naught and E2 are the first order eccentricity at the 2 ends of the column. We can calculate where E2 is greater than EO2 is greater than EO1. As we go into example, you understand that accidental eccentricity can be given by this expression V into L naught over 2, where L naught is the effective column height which we have calculated. Now, V can be calculated by this equation. But remember, V must be greater than 1 over 200. L is the height of the column itself. So a conservative estimate for accidental eccentricity EA can be given as, you can say EA equals to L naught over 400, which is most the simplest way, L naught over 400. Now the second order eccentricity E2 is an estimate of the deflection of the column at failure and is given by this equation 9. This equation 9, K1, K2 into this over pi. Now, where K1 is given by this expression, It seems long, but it will be simplified. So K1 is given by this expression 1 plus into 0.35 FCK over 200 lambda over 150. We know all these parameters by now. So lambda is the slenderness ratio, phi EF is the effective creep ratio, which we have already defined in our previous lesson. And in most practical cases, equation 9, which is this equation 9, uh, equation 9 may be simplified as thus. E2 is K1 K2 L naught square Fyk all over pi squared 103500 D. So that is what the coefficient K2 is a reduction factor, and it allows for the fact that the deflection must be less when there is a large proportion of the column section in compression. The value of K2 is given. K2 from this equation can be given by this particular equation. Now, where NUD in the equation is the ultimate axial load such that NUD is equal to this whole expression, and N bar is the axial load at the balance failure and for symmetrical reinforcement, and it may be given as this. But the emphasis is this is where we might start making a little sense. To calculate for EK2, the area of reinforcement is required because you need to calculate this M bar and NUD. You can see okay, this area of concrete. Let's look at where the area of reinforcement. Okay, area of reinforcement is required. Now, to get that area of reinforcement, you must already know the reinforcement. So, to make life easy for us, what we do is to do it using as a have a particular arrangement of reinforcement and do it using the iterative method. You're going to use iterative method that you have a particular arrangement and you calculate if it is okay. You keep using the chart until you come to the one that is okay. So that will be demonstrated in this question 2, in this example that we are going to look at. So equation example 2 says a non-sway column of 300 times 450 millimeter cross section receives an ultimate limit state an axial load of 1,700 kilonewton and an end moment of 770 kilonewton meter and 10 kilonewton meter, causing double curvature about the minor axis YY, as shown in the figure beside. The column's effective heights are L naught Y 6.75, L naught Z 8.0, and the characteristic material strength are FCK is equal to 25 Newton per millimeter squared, FYK is equal to 500 Newton per millimeter squared. If the effective creep ratio is 0.87, calculate the required area of main reinforcement for the column. This is the cross section of the column that you're given, and this is the initial arrangement of reinforcement in a symmetrical way. It's like a trial arrangement, and so this shows the load. Remember, the question says that the load, the moment, end moment, 70 kilonewton meter and 10 kilonewton meter, they are causing double curvature. That means when this one goes in this way and this one goes in, it means one of them is a clockwise movement and one of them is an anti-clockwise movement. So the solution is, of course, first of all, we need to calculate the eccentricities. To calculate the eccentricity, we need to start calculating the E01 and E02. E01 is eccentricity at the end of the column, the smaller one. So we take it as minus. We can take this one or minus or this one, but it means one of them is minus because moment. Okay, for instance, now this is minus because moment here is on the negative side. So minus 10, that's why we take this. M1 over NED. NED is a design load which we're told is 1,700 kilonewton. So minus 10 into this minus 10 times 10 raised to power 3. This will give over this give us minus 5.9 millimeter. This is to change the whole thing to, so the raised to power, this minus 10 times 10 raised to power 3, the 10 raised to power 3 is to change the meter to millimeter so that we can give our eccentricity in millimeter to this 5.9. So the same thing at this end of the moment. The moment here is 70 over designed load. So we now multiply this times 10 raised to power 3 to also change to millimeter, and we have 41.12. So E naught is negative since the column is bent in double curvature. I've mentioned that before. So if we go to calculate the limiting slenderness ratio, we want to find out if the column is a short column or a slender column. So we go to the limiting slenderness. Remember this equation A, that limiting slenderness is A times B times C all over square root of n. So we calculate A, which is 1 over 1 plus 0.25 EF. We are given creep ratio, effective creep ratio at 0.87. So when we put that, our A gives us 0.85. And because we are not given W, we take B as 1.1. And so for C, our M, we have calculated MO1 over MO2 is actually minus 10 over 70. I told you why we have minus, because they are bent on double curvature. So if you have 1.7 minus into minus 10 over this place will turn to plus. So we have our C as 1.84. So our N is our design load all over AC, FCD. Design load we have been given as 1,700 kilonewton. While we multiply by 10 raised to power 3 to change it to Newton all over. A, area of concrete. The cross-sectional area of the column is 300 by 450, so that gives area of concrete, while 0.567 is a factor of safety and 25 is a design characteristics load, cylindrical load of concrete. So in that case, our N is 0.89. We now come and put in this equation for limiting slenderness. Limiting slenderness, which is 20 ABC all over square root of n. When we put all these factors, it gives us 36.47. So our limiting slenderness is 36.47. The next thing is to calculate the column slenderness itself. Column slenderness is because the effective length height now is different in both minor and major axis. So we are going to calculate differently. For the minor axis, of course, all of them, the formula is L naught over square root of I over A. For the minor axis, the effective length was 6.75 meter, which you multiply times 10 raised to power 3 to change it to millimeter, all over the square root of I. Remember, I for rectangular section is BH cubed over 12. So this is B, which is a bit, when you are in this minor axis, this is B. This is the H, which we cube all over 12. Now, this 300 times 450 takes care of the area, cross-sectional area. So once you do that, the slenderness in the minor axis is 77.85, which is greater than the limiting slenderness of 36.47. For slenderness in the major axis, we have the same formula. So this is the length, the effective length in the major axis, 8 times 10 raised to power 3 all over the square root of. For in that axis, B is 300, H is 450, which we square, all divided by 12. Then 300 by 450 is the area, cross-sectional area. So once we do that, we have our slenderness in that axis to be 61.55, and it says greater than the limiting slenderness. So we can now say, since both axes, the slenderness are greater than the limiting slenderness, we now say that the column is therefore a slender column, and the most critical axis is the YY axis. So we go ahead to calculate the eccentricity. Remember, the total eccentricity is E naught plus EA plus E2. So the equivalent eccentricity, which is E naught, we are given it has to be either of this expression, whichever is greater. So now 0.6, we have calculated E01 and E02. So 0.6 E02 plus 0.4 E01 is what? 22.35. You can calculate that. While 0.4 E02 is 16.47. We take the greater one, which is 22.35. So our E naught is 22.35. We now go to calculate accidental eccentricity, which I said the easiest way is to do L naught over 400. We are doing L naught Y because that YY axis is the most critical in terms of slenderness. It is the one that had the highest slenderness ratio. So with this, we calculate our accidental eccentricity. What we are now left is E2, the eccentricity due to the second order effect. So the second order eccentricity we give this, remember this formula, K1, K2, L naught squared Fyk all over pi squared 103,500t. So this is the formula that we use, where K1 is this. So we can come to this formula to calculate for K1. This is 1, this is 0.35. F is a cylindrical strength of concrete, which is given as 25. Lambda y is the slenderness of ratio in the minor axis. So when we put all these effective creep ratio, it gave us 0.96, but the formula say that K1 must be greater or equal to 1. So we have to use K1 as 1. Now we take our initial value of K2 as 1 because I said we are going to use trial and error method to arrive at the what is okay. So initial value of K2 is taken as 1. If we take initial value of K2 as 1, we now come to this formula to calculate E2 using the initial value of K2 as 1. So with that, when we put all the parameters, our E2 give us 92.92 millimeter. We now go to calculate the total eccentricity E thought, which is E naught plus EA plus E2. That gives us 132.15 millimeter as a total eccentricity. We now come back to this formula to calculate the moment. The moment is the design load multiplied by total eccentricity. The design load is 1,700 kilonewton. The total eccentricity is 132.17 millimeter, which we multiply by 10 raised to the power 3 minus 3 to change it to meter. So the moment here is now 225 kilonewton meter. So we now go to the iterations. The first iteration, the parameter, let me just show you. This is the column chart. This is a column chart. The column chart here, this axis is NED, design load all over BHFCK, while this one is design moment all over BH squared FCK. So we need to calculate this value. We calculate this value so that when we come to this chart, we are able to take value from the chart. Note that there are different charts. This is a chart where D2 over H is 0.05. In this one, D2 over H is 0.10. In this one, D2 over H is 0.15. In this one, D2 over H is 0.2. So you use that, you select the chart to use based on your D2 over H. And in this chart, we pick up value. You can see these ones, the ones that this curve gives us the value of what? ACFYK all over BHFCK. Those are the value that we pick from this curve, the value that we pick from this curve. While based on these numbers, the lines. While this one, this dotted one, we start K, which is the way we are going to pick our K2. This is when K2 0.2, 0.3, 0.4, 0.5. This way we will take our value for K2. So now let's go back and calculate our parameters. In the first iteration, NED all over BHFCK is the design load all over B is 450, H is 300, FCK is 225. So that gives us that value as 0.504, which you can just take 0.5. The next one, we calculate the component on the horizontal axis, which is M all over BH squared FCK. M we have calculated a moment to be 225 kilonewton meter. We multiply by 10 raised to the power 6 to change it to Newton millimeter. So our B is 450, H is 300, which we square FCK is 25. So if you do that, you have 0.222. So now let's calculate our D naught over H. How do we D2 over H? How do we know D2? This is the height of the column, which is 300, and we are told D effective depth is 240. That means the other D2 will now be 300 minus D, which is 60. So that is why we come here. We say that in our first iteration, our D is what? 60. Our H is 300. So over 60 over 300 is 0.2. So we now go to the chart of D2 over H2 equals to 0.2, which is this chart. So this is the chart that D2 over H2 is equal to 0.2. So in this vertical axis, our N over BH here gave us 0.504, which we can take as say 0.5, and this is 0.5. This is 0.5. In the horizontal axis, our MED over BH squared FCK gave us 0.222. So we can come here. This is 0.2. From the way this is calibrated, this is 0.2, this is 0.21, this is 0.222. So 0.22 should be about this place. So 0.22 is here. So we now produce the line vertically to meet 0.5. So we have something here. So this is where we have a point. From this point, if you read this curve, that point here, this line is 0.8. This line is 0.8. So this line is 0.8 from where we are looking. While we are here, by approximation, this should be 0.88. Another person might just see it as 0.89 or 0.87, but I'm saying 0.88. That's why. So I now take our ACFYK over BHFCK as what? 0.8. Take note of that. Then we need to pick another value for K for the second iteration. So this is the point that we are looking at. We are somewhere here. So in this, if we are somewhere here, So if we are somewhere here, this is 0.7. So this should be about 0.73 by my own reading. So it should be about 0.73. Okay, sorry, we are somewhere in this place. Let me look at it again. So if we are somewhere in this place, if this is 0.72, this place can be taken 0.73, or maybe someone else might present as 0.72, but I saw 0.73. So that means that K2 is 0.73. So let's go back there. That is where we say from that chart, design chart, our ASFYK over BHFCK is 0.88. Our new K2 is 0.73. So with that, we can now go to the second iteration. In our second iteration, we still go back to this formula to calculate for E2. But in this case, K2 will not be 1 again. K2 will be the new value of 0.73, which we have gotten. So we now put in that. You can see that this is the same equation, D and all those things, but K2 is now 0.73. That gives us a new value of E2 as 67.83. So we now use that in our second iteration to calculate for total eccentricity. E1 is still 0 is still the same, E is still the same, but E2 have changed because of the new value of K2. So that gives us a new E thought that is total eccentricity as 1.07. We use that to calculate the moment again like we did before. Our new moment is now 182 instead of 2. I think the previous one was 225. This is 182. We now use 182 again. Our NED all over BHFCK will still be the same, 0.504. But our M all over BH squared FCK will change because of the new value for the moment. And the new value for this component gives us 0.18. We now still go back to the chart, the same chart of D2 over H is equal to 0.02. We go to that chart again to find. Remember, our new M over BH squared FCK is 0.18. So we go to that chart and come again. Our this in vertical axis is still 0.5. But in the horizontal axis now 0.8. This is 0.15. This is 0.16, 0.17, 0.18 is here. So we now produce the 0.18. We produce it to meet the 0.5. This is 0.1678. We produce it to meet the 0.5 somewhere around somewhere below to this 0.5, 0.6, 0.7, 0.8. So if we produce 0.8 it's to 0.5, it is somewhere around here that we find ourselves. And when it is let's let the cursor come again. So this is 0. This is 5, 0.6, 0.7, 0.8 is somewhere around here. So being here now, we can take what is the value for our this AFY over BHCK, which is this lines. So if we are here, we can take if we are here, we can take our family that to be 0.69 because this is 0.6, this is 0.7. So here will be somewhere around 0.68 or 0.69, but I took 0.69. Then our new K2 for that place, our new K2 in that case is 0.68 because this is a K, this is 0.6. This place should be from here 0.7, this is about 0.68. So we take a new K2 at 0.68. So that is why if you go back here in our second iteration, ASFYK over BHFCK was 0.69. Our new K2 is 0.68. So we go to the third iteration. In the third iteration, we calculate the new eccentricity again using K2 as 0.68. So that gives us a new eccentricity as 63.19, which we go back to calculate the total eccentricity again and it gives us 102. We go again to calculate the new moment. The new moment gives us 173.4. So we go ahead, NED over BHFCK will not change because none of the parameters have changed, but M over BH squared FCK will change because M, the moment have changed. So if we go back to the design chart and check from the design chart and check the chart of D2 over H is equal to 0.2 before the value, these two values again. So let's go and see. So in this case, this horizontal line is 0.17 and 0.17 is somewhere here. This 0.6, 0.17. So if you produce it to 0.5, you will have peak value there. So the value we pick was that this ASFYK over BHFCK is 0.68. The new K2 is 0.67. Now, if you look, the new K2 0.67, while the previous one was 0.68, the value K2 is not changing much again. So we can stop at this third iteration. Once we stop, we now go and adopt this ASFYK over BHFCK is equal to 0.8. This is what we are going to use to calculate our area of reinforcement, which we say, okay, if this is equal to 0.8, that AS, which is the area reinforcement, will now be BHFCK all over FYK, which is this 0.68 times 450, which is B, times 300, which is S, FCK is all over FYK, which is 500. And so our area of reinforcement is 4590 millimeters square. Now, this is where the question stops. But in practice, when you have this, you now find the arrangement of reinforcement that will give you this area of reinforcement, and it will be okay. So the rest is just a design chart which we have looked at. This is a design chart for D2 over H equals to 0.05. This is for 0.1. This is for 0.15. This is for 0.2, which we have used. So thank you for watching the video up to this point. Please remember to follow this channel so that you'll be getting subsequent video on structural engineering. Thank you very much.